day 2 of the 5-6 notes, where we're going to be moving into some calculus with our inverse functions, and we are going to be taking the derivatives of the inverse trig functions. So first thing, we've got 3 that we're going to derive, 2 in your notes and 1 on your problem set. And the 3 that we're going to derive are the 3 non-cofunctions, because if you look at the chart on the next page, the cofunctions are just opposites. So cofunctions, for example, cosines, arc cosine's derivative, arc cosecant's derivative, and arc cotangent's derivative are all just the opposite or negative of these over here. So we're going to go and derive the model for finding the derivative of arc sine. So u is some function of x, as always. Maybe it's 8x minus 1 or 4x squared plus 2 or root x. But u is, as usual, some function of x. And what we're going to do here is derive the model for how I take the derivative. So eventually I want to figure out what is y prime if y is arc sine of u. So the first thing I'm going to do is take sine of both sides to pop that u out. Sine of arc sine u is just u. What I know then is that the sine of some angle is u, or u over 1, and sine is opposite over hypotenuse. So when I go to my little triangle over here and I call my angle y, I know that the opposite is u, and the hypotenuse is 1, and I can get the adjacent side by thinking of the Pythagorean theorem that a squared plus u squared equals 1 squared. So a squared would be 1 minus u squared, or the square root of 1 minus u. So back over here to my workspace, I'm going to take the derivative of both sides with respect to x. Another notation for du dx is to call it u prime. The derivative of sine y is cosine y with respect to y, but when it's with respect to x, I have to multiply it by the derivative of the guts. A little implicit going on here. I'm going to divide both sides by cosine y. I'm going to go back to my model and get cosine y in terms of u or in terms of eventually x. Cosine is adjacent over hypotenuse. So when I do adjacent over hypotenuse, I end up getting square root of 1 minus u squared over 1. And so I've derived the model for finding the derivative of arc sine of any function. And you'll see on the next page here, when we turn it, I've got the chart screenshotted from your book, and that is indeed what it says you use. But I like to show you why. I don't like you to just memorize things. So we're going to derive one more, and then I'll leave the arctan one for you to do on the problem set. So in a similar fashion, because that was so much fun, we're going to take the derivative of arc secant u similarly. So I'm going to start off by taking secant of both sides. So I know that the secant of some angle is u, because remember, secant and arc secant are inverse functions. So on the right-hand side, it's like you're squaring a square root. You're doing secant of arc secant. So I get secant y is equal to u. So here's my y. I know that secant is u over 1. Well, cosine is adjacent over hypotenuse. Secant is cosine's reciprocal function. So I know that the hypotenuse over the adjacent is u, or u over 1. What that means is over here, I'll get the square root of u squared minus 1. So now let's go back, and similarly, we're going to take the derivative of both sides with respect to x. And remember, my goal is to figure out what y prime is. I am again going to call du dx. I could leave it as it is, but I'm going to call it u prime just for smoothness of working with it. The derivative of secant of a function is secant. Tangent times the derivative of the guts, which would be y prime, and remember that's what I'm trying to figure out, is if y is arc secant u, what is its derivative? So I end up with y prime is equal to u prime over secant of y times tangent of y. So I go back to my picture, and my secant is hypotenuse over adjacent, which is just u, or I already have it defined up here as well. So I have u prime over u. Tangent of y is opposite over adjacent. So that would just be the square root of u squared minus 1 over 1. And so if you flip the next page, you'll see that exact thing, only they'll have absolute values around the u, mainly because hypotenuse cannot be negative. Anyway, so down here on the bottom it says one of the others is on your problem set, so you can bet you're going to be deriving the arctan model as well. So here they are all listed. This isn't something that you need to have mastered. This is just primarily exposure. We work more with these in Calc 2 than in Calc 1, but we're going to have an assignment and a problem set, but no test on these. So the first one, the derivative with respect to x of arcsine u is u prime, which would be 2 over the square root of 1 minus u squared, which would give me 4x squared. And one can be as easy as that. Arctan is this model. They all have u prime on the top, by the way. So all of them, you take the derivative of that inside function. They all have the cofunctions being the opposite of the originals, so that's kind of nice. These are the two up here that if you were to see, it'd be one of these. The way I remember it is arcsine's the uglier of the two. It's got the root and the minus. Tangent's the prettier of the two, no root and a plus. So that's kind of how I keep those in my brain. Arctan is a little prettier. It's nice and tan, and it's got u prime on the top, no root, and a nice plus u squared on the bottom. And that one's done. It's nice and easy. You just use the models. So arcsine u, again, this is the uglier of the two. They all have u prime on the top. The derivative of x to the 1/2 is 1 over 2 root x. This will be the uglier one, so it's got a 1 minus and it's under a root. And then I do u squared, which is just an x. So when I get rid of my complex fraction, which is always a good thing, I will collapse that down, and then I will wrap that product down there in under 1 root, and it would be done. And I'm not going to do letter D. You kind of get the hang of it. So now what we're going to do is just a few examples here. So my goal is to figure out what y prime is. That's what this would say. Find the derivative. The derivative of y with respect to x will be the derivative of this whole sum. The derivative of a sum is the sum of the derivatives. The derivative of arcsine is u prime over square root 1 minus u squared. In this scenario, u is x. Then I have plus, and now I've got a product rule. So I do first times derivative of the second. So I'm using my power rule. I'm also going to use my chain rule, and remember to multiply by a minus 2x times the derivative of the guts. So that's first d second plus second d first, which would just be 1. Obviously, this needs a good cleanup, so I'm going to leave that first part of the sum like this. I'm going to go consolidate. My 2's are going to cancel. I'm going to have a minus. I'm going to have an x squared up on top with this x times this one. My negative 1/2 power is going to drop down to the denominator, and then up here I still have this. It's getting better, but it still needs a little work here. I'm going to get a common denominator. I've got 1 minus x squared already able to be written with a common denominator. Now I'm going to do my crisscross. So I've got 1 minus x squared minus, plus is my link. This would be square root times square root will undo each other. And then that would be all over 1 minus x squared. When I clean that up, what I will see, whoopsie, is a 2 minus 2x squared over the square root of 1 minus x squared. So if you don't see the answer in the back of the book isn't exactly what you got, the odds are is you just need to kind of keep working it and consolidate things, get rid of negative exponents. Sometimes there might be some factoring. I could factor a 2 out of the top here, but it does not cancel with the bottom, and it doesn't necessarily make it look any better, so there's no need to. So moving on to the next page, we've got a question we've had in here a million times. Sorry. Anyway, slope of the, or equation for the tangent line always requires a point. Got one. So it'd be y minus the y I know, y minus pi fourths is equal to the slope there, which needs to be found, times x minus the x I know. So the only issue is I need to go figure out what the derivative is at that point. So I start finding my y prime. I'm going to launch into the product rule, and I'm going to do first d second, which is u prime over, signs the uglier one. It's got a root and a minus. So that's first d second plus second d first. And there's no need for me to clean this up because I want a numerical derivative. I want to figure out what is it at that particular point. So instead of risking making a mistake cleaning it up, just leave it because you really just want to get its value. So I'm going to go replace. This derivative is explicitly given in terms of x. So I've got 3 times 1/2 over the square root of 1 minus 1/2 squared plus 3 times arcsine 1/2. And what I'm going to do now is go and clean that up because that's a big ugly mess. So on the top of this fraction I have a 3/2. On the bottom I have the square root of 1 minus 1/4, which is the square root of 3/4, which is root 3 over root 4, which is root 3 over 2. And then these cancel off, or you can think of multiplying by the reciprocal, but that big ugly mess ends up being 3 over the square root of 3. Over here, arcsine 1/2 is, basically I want to know the sine of what angle gives you 1/2, and that's pi sixths. And when I triple that, I end up with pi halves. And again, you might not see this simply because although you don't need to rationalize the denominator, you need to recognize when it has been done. So if this were rationalized, it'd be 3 root 3 over 3 or just root 3, and that does make it look an awful lot better. So I'm going to rationalize the denominator. So the slope of my tangent line at that point is root 3 plus pi halves. And I'm not going to go make that a decimal or anything. Keep in mind, if I leave it as it is, it's technically not right. It's got a syntax error because I really do need the parentheses around this or it will not be numerically valid. So the assignment was this for 5.6, and the p-set's also attached in Edmodo. Notes are just fine on this section. So have a good one.